The next presentation will be given by Rafael Neto Henriques. He's a research fellow at Champalimaud Foundation in Lisbon, and he's going to talk to us about diffusion imaging in Python DIPY and its contributions to open and reproducible research.
So, as Rita Nunes said, my name is Rafael Henriques. I'm currently a postdoctoral fellow at the Champalimaud Foundation in Lisbon. However, have been contributing to DIPY since 2015 when I was a PhD student at the University of Cambridge. So nowadays, medical imaging is in rapid evolution, and this is with the goal to improve its sensitivity and specificity, to obtain more accurate and early disease detection, better treatment decision, and this goes in line with ideas of personalized and precise medicine. As we heard from previous talks, namely the yesterday's talks, there's also some efforts to enhance imaging accessibility and safety. So this leads to demand for advanced software to enhance image quality and analysis. And this should have some desired aspects. So it should allow for rapid and dynamic development to allow following up the latest innovations. It should be accessible, provide robust algorithms, standards that promotes the use at different systems and also at different applications. So I strongly believe that with open source software, we can better achieve these aspects. So first, because this promotes collaborative development, and it's only in collaborations that we more easily can have softwares that are more dynamic and following up the development of medical imaging. They are free and open access. They are transparent and follow reproducibility aspects, and this promotes the robustness of algorithms. And also in the new community is the best way to decide which standards to use to be compatible with different systems and with the desired applications. So what you will expect in this talk. So I will talk about DIPY. I will mention its collaborative and inclusive environment, its code transparency, and what reproducibility standards we use. And then I will also talk about some usage examples, and I will finalize my talk with some final remarks. So DIPY is a large-scale collaborative open source image software library. So it has codes and algorithms specialized for diffusion MRI, including from early steps of pre-processing, from signal reconstruction, where we have several different diffusion MRI models. It also has a focus on tractography, have unique algorithms for tractography segmentation and streamlined registration, and also it has specific diffusion MRI statistical analysis and tractometry. Also to point out that some of our algorithms, for example, for data visualization, tissue segmentation and classification and data processing can be applied to general imaging modality. So DIPY also has a general use in general medical imaging. So talking about its community, so DIPY brings together scientists across labs and countries. Its first release was around the end of 2009. And now, nowadays, we have more than 100 contributed from more than 30 universities and institutions. Just to mention the three top contributors of this of DIPY. So we have Eleftherios, that was the founder and is the leader, lead developer. Ariel, that became the associate lead developer, and Serge, that is the DIPY release manager. So DIPY source code is available in its GitHub repository. Everyone is free to use it. So to install it, it's quite easy. Just in your terminal, you can write pip install DIPY. And everyone is also free to report bugs on the issues or contribute with new feature or even try to fix any bug that the user might found. So just to give an idea of the usage, how we can use DIPY, I'm here showing a typical workflow for reconstructing diffusion MRI models. So the first way that you can use DIPY is using a Python scripts or create Jupyter notebooks. And to just give an idea how the code, the library is organized, I'm giving some example of code for reconstruction of DTI. So DIPY has functions to load the raw data and important imaging parameters for model reconstruction. For DTI, it's the b-values in gradient directions, or b-vex. And in the core of DIPY, we typically summarize this acquisition parameters on the gradient table object. And then you can follow with processing. We have several algorithms in there: DIPY align, DIPY denoise, and segment. And I'm just showing here a case of the denoising using a PCI approach. And then after preprocessing, you can call your model from DIPY reconstruct. So in this case, DTI. And basically what you have to do is define your model according to your gradient table, and then you can fit the data and obtain parametric maps. In the case of DTI, I'm showing here the well-known fractional anisotropy. So to adapt this to another different models, you can use a very similar structure. So in the following example, I'm adapting the code for diffusion kurtosis imaging. So you can follow exactly the same steps, but now you have to call your model of interest, DKI in this case. And here I'm just plotting here the standard mean kurtosis tensor map, which higher values correspond to brain regions of where non-Gaussian effects are high. Of course, in this talk, it's impossible to show all the models that we have, but just to have an idea, I'm presenting here this diagram with most of the diffusion MRI models that we have. So again, you can just adapt your codes to use one of these techniques. And another way also to use DIPY is with its command line interfaces. So for example, if you don't want to write your own scripts and you want to fit DKI, you can just write in the terminal DIPY fit DKI and indicating where is the path of your data, and it will process everything for you. To see what other available interface that we have, after installing DIPY, you can just write DIPY info.h, and it will give you a list of the current interfaces that we have. About the code transparency and the reproducibility standards, to note that all DIPY source code is openly available in its repository. So this is the idea of DIPY is to be a library and not the pipelines, and no code is wrapped from party software. All code is also well tested, so we use unit tested and continuous integration to make sure that anything, for example, nothing breaks after a release. Just to give an example of how this is done, a test for DPI. So basically, the idea is that we produce some simple simulations with all ground truth parameters known, and then we can calculate independently on the fits the ground truth model parameters and also the expected signals giving acquisition parameters, so b values and directions. And then, so what it's done under the hood is that we test on this synthetic signals, compute the metrics, and see if they correspond to expected ground truth. So this is especially done before a release to make sure that everything is compatible, for example, to new releases of Python, or that we didn't break anything when developing novel things in DIPY. Okay, so as I said, DIPY can be used also for tractography. And so here is a workflow for tractography. So the first early steps is exactly similar as I presented in the previous slides, but we typically now use a model that reconstructs orientation distribution function. So I'm showing here orientation distribution function maps for a new model called Roomba. And then after having these ODFs, DIPY has the functions to extract directions from these ODFs in mind of probabilistic or deterministic tracking. We have also functions to define the starting points of tracking and the stopping criteria conditions. We also have the algorithms for performing different types of tracking and streamline generation and to save tracks. And then after that, we can go through visualization. This is an example of a corpus callosum track reconstructed in top of a T1 weighted image. This was produced using DIPY code. And then if you want to do group comparisons, we also have tools for streamline registration and also tools to assess along tracks difference across groups. But to have the full code of how to use all of this, you can find the tutorials in our official webpage, dipy.org. So also DIPY is one of the pioneering libraries that have tools for processing advanced diffusions data or data acquired using advanced diffusion sequences. So basically in the conventional diffusion MRI, we acquire each image for a gradient direction and p-value. So with advanced diffusion sequence, we might acquire each volume after probing a space or several directions at the same time. Using one of these gradient profiles. And in this case, then the image cannot be characterized by a single p-value in gradient direction, but by a bit tensor. So under the code, what you basically have to do is indicate not only the magnitude or the p-value in the main direction of this tensor, but also its shape. And this is done using this way. This was led by Levi Karkela. And then you can produce compute a model called the key trajectory imaging model and obtain unique maps as the microFA. That is basically a version of FA that is confounded by fiber dispersion effects. And there are several studies, here some examples showing that this can characterize microstructural changes independent by fiber dispersion confounds, for example, providing better measurements. For example, if you want to study changes on areas that contain crossing fibers or areas of fiber dispersion or even gray matter. We also have a unique technique to process double diffusion encoding data. So double diffusion encoding data, you acquire data after applying two pairs of gradient directions and intensities. And for that, we have the correlation tensor imaging model that was proposed to try to provide more specific information about diffusional kurtosis. So for example, we split the total mean kurtosis maps into a KN ISO source, basically containing the micro FA information that I discussed previously, the KN ISO, which captures the variance of diffusivities inside each voxel, and then there's a K micro that capture microscopic non-Gaussian effects, for example, effects from the variance, the cross-sectional variance of cells, or effects of exchange. And just to have a highlight of what this can be used. So for example, it was recently shown that K micro increases and K ISO decrease provides a signature of cell beading and swelling of ischemic stroke. And so basically the K micro increases is basically what is explaining the previous observations of increased non-Gaussianity on ischemic stroke. And this goes in line with expected effects of swell beading and swelling. So in DIPY, we have a code for this, and this was developed this summer in the Google Summer of Code. So if there's any student interested also getting involved next year, please contact us. So in this technique, since we have now two pairs of gradients, we have to define two gradient tables, but then the structure follows always the same as the previous standard diffusion MRI techniques. Okay, so apart from the versatility of techniques that we have in DIPY, it's important to note that DIPY is being used by other public projects. I just want to highlight a few. Of course, it's impossible to highlight all of them. But first, I want to highlight Furry that is being developed by some of the members or the community of DIPY. So this was kind of a side project that was born from DIPY. And the objective is to provide open source library for scientific visualization in 3D animation, and also have tools for visualization of diffusion MRI data as tractography results. There's also the DSimPy, that is a diffusion MRI Monte Carlo simulator. QSI Prep, that configures pipelines for processing diffusion MRI. It includes the techniques that DIPY implemented together with other softwares as FSL and Henriques. And then we have the 3D slicer, the desktop software that the diffusion part uses a lot of what we have in DIPY. And then there's all other mentioned. So for example, there are some efforts to accelerate DIPY using GPU, DMPy that specialize in advanced diffusion, microstructural diffusion models that also use calls our functions, PyFAQ to a long track diffusion analysis. And we just had a talk about UCAT in Ukraine. So how to get in touch with our community? So you can subscribe to our mailing list. We also have a forum under our GitHub, and we also have an iterative Gitter chat room. Also, another way to get to learn more about DIPY is we annually organize a workshop. In this workshop, we have the contributors doing tutorials of DIPY, and we have scientific sessions, and this is some of the distinguished speakers of the workshop of the following year that is in March, and registration is open. So just to wrap up, I show in this talk that DIPY is an open source imaging software library that specializes in algorithms for diffusion MRI, but it can also be used for general medical imaging. And then going back to the desired aspects of open source software, DIPY is a collaborative effort from developers from different institutes and universities across the world. All source code is openly available in DIPY repository. I also showed that all code is well tested. It's compatible to different MRI scanners, and it can be applied to different applications, and I showed here some of them during this talk. So to finalize, I want to thank my funding agency, my institution, the DIPY contributors, its sponsors, and I want to thank you for the invitation of being here today. Thank you.